Welcome back to this episode of making 3D printed plastic do what it shouldn't be able to do. If you haven't seen the last episode, I highly recommend you check it out to have context for this one. But where we left off last time, the cart drove around just fine. The external gearing would tend to slip on corners, which was unfortunate, and it didn't quite have enough torque to be able to drive me around comfortably. Which wasn't actually the original goal of the project, but seems to for some reason be the benchmark that I set for myself. I also wanted to improve the reliability of the gearing system. There were times where the gears would shear off. So in the last episode, I promised that I would be developing a planetary gearbox for the cart. And that's what this episode is all about. The first design that I came up with was a stackable design. I wanted it so that I was going to be able to add or remove stages as I found necessary. I thought this was pretty clever, but later on I realized that I was going to need to make it a whole lot more compact to be able to fit 4 on the cart. Another interesting part about the first design was that in order to save some money, I decided to try out some PTFE bushings instead of running a bearing for each of the individual planet gears. I felt like that might be a pretty good way to make a gearbox that was very cost effective, and since everybody has a bunch of that PTFE tube hanging around, should be a good solution. And naturally, because I got a new 3D printer, I got all gung-ho and decided I would reprint all of the frame parts out of some black PETG with this cool external design. And I also went right ahead and printed out 4 gearbox to give it a try. In hindsight, this was quite dumb. I pretty much just wasted a bunch of filament because it turns out that you need to test these things before you go into mass manufacturing. But at the time, I didn't know that, so I assembled everything up and gave it a test. I also made this super nifty electronics mount plate instead of the 3D printed trays I had before. Now, I honestly forgot to film testing it, but it didn't work that well. One of the main issues I've had since the beginning of this cart is just misalignment between the wheels and the gearboxes. So I decided I would make a version 2 that hopefully constrained the gear train a bit more so that it couldn't move whenever the cart frame flexed. I also thought that maybe I should do some reliability testing. So version 2 quickly became version 3. Turns out she can't lift 12.5 pounds, but not for the reason. Which became version 4.
Notice that we actually broke off one of the pegs. So I will be setting.
Which became version 5. Which became version 6? Okay, I think you get the point. Let's just roll the carnage. See this pin here melted? Slash broke. So while it was still working, it was pretty close to failure. So as you can probably tell, the main issue there I was having was heat. So I decided that I would try out some bearings to reduce the friction inside the gearbox on each of the Planet gears. This of course meant I had to spend more money, which as you can probably tell I'm allergic to, but I thought I'd give it a try. I also decided to print the pinion out of glass reinforced nylon, which should have really good temperature resistance. Gearbox test number 452. So this is with the glass fiber gears, ABS carriers, and it's all lubricated. So let's give it a try. Oh, and it has bearings now. Ready? 3, 2, 1. Dramatic failure there. So let's take a look. Ready for the carnage? Ooh, ABS smoke. So no surprise there. Glass fiber gear is like not even touched. Ooh, that is a hot bearing. Explosive results. So after that, I decided to add glass fiber nylon gears to the entire first stage. And finally, I managed to crack the code. Seems to be able to run for over 10 minutes now with no problems at all. Oh yeah. So yeah, it was still getting real warm, but the material choices finally worked out to the point where it was not melting during operation. So I was pretty happy with that. That was with pretty minimal lubrication, so I thought if I add some lubrication to the final version, that would give me a bit of a factor of safety on the design. So I printed out 4 versions and started to assemble. As you can probably see here, we still have quite a few bearings in the design at this point, but there is 2 stages. The first one has a polycarbonate planet carrier, the second one has an ABS planet carrier with ABS gears, and the first stage gears are all glass fiber nylon. The ring gear inside of the case is polycarbonate, and then everything is held together using some small plastic screws. I also removed all of the shields off of the bearings since they're going to be bathed in grease anyways, and I figured that this would reduce the friction in the bearings a little bit, so when they're spinning extremely fast from the DC motor, they're less likely to overheat. And yeah, the final step in the process was to lubricate everything, so I used some light oil on all of the bearings just to make sure that they were packed full, and then I packed the entire case full of this sort of medium axle grease. It was what I had on hand, and it seems to do the job pretty well. Likely going with a lighter grease would have been a good idea, considering how fast this spins, but to date I still have not had a single internal failure. Please let me know if you want me to post these files along with the bill of materials online. There are fairly strict material requirements, but since everybody and their mom nowadays is able to print almost any 3D printed material, I think that most people would probably be able to manufacture this one at home. I've pretty extensively checked it and tested it, and it seems to work quite well. So, since I was finally happy with the design, I made the remaining 3 and mounted them up to the cart. And because I'm a glutton for punishment, for some reason I wanted to try tracks again. This time, since I was able to print TPU better, I thought, well, what if I was able to make a tracked version of the cart with just some simple TPU tracks that would run across the 2 main drive wheels. Rather predictably, this was really dumb, and it immediately detracked. And I decided, you know what, I didn't want to go back into another escapade of trying to make tracks when I was just trying to get the project done at this point. Besides, anecdotally, in the scientifically accurate burnout test, I didn't feel much difference between the tracks and the wheels. Last thing that was left to do was just to finish up the electronics and wiring because it was currently a bit of a rat's nest. So I soldered up some new wires for it and made some electronic mounts that would mount on that large electronic mounting plate that I made earlier. So, and then the final thing that I felt was still an issue was the misalignment between the gearbox mesh and the wheel mesh. When I would load up a lot of weight on the unit and I would go to turn left or right, the gear meshes would become misaligned slightly and then the gears would skip. Now, most of this was due to slop in the bearings and the axles of each wheel, but I didn't currently have any machine tools to fix that, so I thought I would give a belt drive a try. This time around, I actually used a correct style of timing pulley design, and I 3D printed each of the belts out of TPU. And I was going for a max load test. Now, I knew from previous testing that the gearboxes were able to go max load in a stationary setting like this without slipping or breaking, so I wanted to give these ones a go. Unfortunately, I never really got this to work correctly. The belts would basically just stretch out after the first use and become garbage after that. I even tried to 3D print some out of PLA. I tried to print some with a PLA or ABS or PTG strengthening ring behind them, and nothing really worked out, so I gave up on the idea, and instead, I spent $1,200 on this. Oh, and the other thing that I did is that I switched over to a herringbone gear output, and I was hoping that this would provide sort of a self-centering thing. But besides that, I started to machine new shafts. So besides my lack of skill, knowledge, machine rigidity, and ability to film this correctly, I did end up getting some okay parts, if you ignore how horrible the surface finish is. I machined them out of 1018 steel, and 1018 steel plus a mini lathe equals maybe acceptable results if you squint really hard. So this lathe is of the Chinese persuasion and is definitely going to need some upgrades to make it a bit more serviceable. Plus, I'm going to need to learn a lot. So if you're interested in a video of me upgrading the lathe, please let me know in the comments and we can make that. Sub-tenth of a millimeter isn't awful, right? Another thing I did during this time was I replaced all of the PETG frame components with glass fiber reinforced ABS, just to give it a bit more rigidity. With the shafts done, my next step was just to machine down the ends of all of the aluminum parts I had cut earlier to get them close enough to dimension. Before I was using a saw, so naturally the cuts were not exactly straight and they were not exactly flat, and they were also all off by a millimeter here, a millimeter there. Then it was time for what I hoped and prayed was the last time I was going to have to rebuild the cart. So I assembled up all of the machine parts that I had made before, which were fitting up a lot better than when I was just sort of freeballing it with a saw. And finally, I actually went out and gave it a test. So I threw on one of my dad's hydrofoil boards just to see, because it's one of the heavier boards he owns.
Good.
And as you can see with all of that mass up high, we had some front to back wobblies. But it actually drove around pretty good with all the weight on it, which was a huge success. Right after that test, however, I actually moved. So this was my old shop. It was extremely congested. I had way too many projects and machines. and it was a little bit overwhelming to do any work in here, which kind of killed my motivation, hence why I am the slowest uploader ever to live. So I'm going to save the shop tour for a future video, but just know I have a lot more space for potential upcoming future projects. Okay, so back to the car. So actually that last test went okay, but I wouldn't say amazingly. So I ended up shearing off the end of 2 of the drive gears, which was rather unfortunate. So I knew that I was going to have to do one final change to these damn gearboxes. I can't even tell you how many iterations that there were. I lost count. So I disassembled it again, and I took a look at the broken part. So clearly you can see from this that just the end gear broke off, and that's because there was not a lot of cross-sectional area between the outer bearing and the inner bearing on that particular stage. So I bought smaller bearings. That allowed me to get a good amount more cross-sectional area on those frontal gears where the torque is the highest. But that also does mean that these gearboxes now feature 5 different types of bearings on the inside. Not a great design. And I figured it was a good time to also take a look inside the gearbox and make sure that only the front gear had broken. But as you can see here, the rest of it was basically in perfect shape. So I rebuilt the remaining 3 with the exact same change so that all of them would be bulletproof, even the ones that didn't break. And then I moved on to the final change. So the final thing that I wanted to do was to increase the overall length. As you saw from that video, there was a lot of front-back wobbliness with that hydrofoil board on there, which I didn't really want. So I made pieces that would extend the frame. It was pretty simple. So I will spare you watching me rebuild this thing for the 30th time and just show you sort of what the final result looks like. Essentially, we have those small pieces I made, plus these crossbars that went in between to hold it all together. Seemed relatively rigid, especially once I put the electronics plate across the bottom. And I finally added a switch to the top of the thing so I wouldn't have to flip it over and remove the battery every single time. And then I cleaned up the wiring one last time and 3D printed this little cover that kept everything hidden and made it look a lot better as a final product. Now that I had hopefully fixed all of the mistakes I had made in that last test, it was time to drive it around my yard and see how it worked. Now, I don't own any surfboards, but I figured I would do my best to simulate one, and I would drive it around and just see if anything broke. Seemed to drive around pretty good with no load, so I thought I would throw a 35-pound winter tire on top and give her a go. No problems really, so the last test was just a good little endurance test. Just gonna drive it down the hill and back up again. So I know that this project may not seem like much, and to be honest with you, it really wasn't, but I was so busy during the time I was building this that it almost took me a year and a half. Now I'm super happy that this project is finally done. It was such a long time that I really lost motivation towards the end. I'm really looking forward to building some new stuff. think it is time for the end of the video. Thank you for watching. I think it's fast. I think it's powerful. I think it drifts. That's all I've ever wanted. Thanks for watching. See you in the next one.